Good morning. All right, we are moving along with sources of magnetic fields, right? So we're talking about current carrying wires. Somebody asked last time if there was a good simulation that showed magnetic fields around wires. I did a quick Google search. I didn't see anything that was great. Um, there was one from Khan Academy, a video from Khan Academy, where they kind of overlaid a picture of a right hand around a loop of wire, and then they drew in some field lines and talked about why that looks like a bar magnet. But I really didn't see any good simulations that could help you visualize. But do a little search, see if you find anything. If you do, let us know. All right. So where we kind of left off was that the a wire, right, a current carrying wire, and you sort of have to uh, understand that the wire is going to have magnetic fields that encircle it. So we have a current carrying wire, like we drew it. We drew it perpendicular to the plane of the page, I think, last time. So let's start with that one. I coming out of the page, a long wire perpendicular to the plane of the page. What direction? We know, right? You got to start with something. We know the magnetic field forms circles around the wire. Question is, does it go counterclockwise or clockwise? We use our right hand rule, put our thumb in the direction of the current, and our fingers curl around in the direction of the magnetic field. So if I put my thumb in the direction of the current out of the page, my fingers will curl around the wire in the counterclockwise direction. So my magnetic field would be something like this. And if I, of course, reverse the direction, I into the page, put my thumb in the direction of the current into the page, and my fingers curl around that wire in the clockwise direction. And as we move away from that wire, the magnetic field drops off. We'll see it drops off as 1 over R. We'll see that today. Now let's shift this whole thing by 90 degrees and look at the wire from the side. So we want to draw the magnetic field in the plane of the page, at least. Let's not worry about 3 dimensions. In the plane of the page, what's the magnetic field doing? Can you draw that in? Right? We know it forms circles around the wire. So we need a happen to have a stick handy. Okay, so it forms circles around the wire. So if we're looking down the wire like we are in one of these cases. Okay, so let's take the one on the left. The current is coming toward the camera down the wire. Current's coming toward the camera. We put our thumb in the direction of the current, and we know the magnetic field forms a circle around the wire. So if I was standing with my magnetic field sensor above the wire and the current was coming toward the camera, what direction would the magnetic field point? It would point to the left, right? It's forming circles this way, right? So if I was over here at the tip of my finger, what direction would it point? Down. If I was underneath the wire, it would point to the right. If I was on this side of the wire, it would point up, right? You get the idea, okay? So now we're taking this and we're rotating it like this. So the current is going to the right. And we want to know if I'm standing here, what's the magnetic field doing? And if I'm standing here, what's the magnetic field doing? The magnetic field anywhere above the wire, the magnetic field is out of the page, right? And anywhere below the wire, the magnetic field is into the page. Okay, we good with that? You got to get in the habit of thinking about things different ways. Move the wire 90 degrees. Okay. So what we want to do is take our wire and bend it into a circle. Right, we want to take our wire and bend it into a circle so we have a current in our circular wire. Okay, if I'm standing in the middle of that loop, what direction is the magnetic field pointing? Out of the page. You see that? Because just pick a tiny segment of the wire. Let's just focus on on this little segment right here at the bottom. What direction is the current flowing? The current is flowing to the left. So remember, when we had a current with a wire, straight wire with the current flowing in it, we said everywhere above the wire, it was out of the page, and everywhere below the wire, it was into the page, right? Right here, where was it? Right here. So that's what we've got there, right? So the magnetic field is going to be forming little loops around it. Oh, let me draw that a little differently. The magnetic field is going to make a little loop around it where it goes up on the inside and comes down on the outside, right? Another way of drawing that is a dot on the inside and a cross on the outside. I'm trying to draw a loop in 3 dimensions and 2 dimensions. Now let's rotate ourselves around to a different area. Let's maybe over here. Let's look at this area over here. What's happening over here? We've got a current that's flowing basically down. Every place to the right of that current path, the magnetic field's coming out of the page. And every place to the left, it's going into the magnetic field, I should say, is going in and out, right? Why is that? Because it forms loops around, right? It makes a circle that comes up on this side and goes down on that side. Does that help a little bit? We're putting our thumb in the direction of the current, right? So it's the same thing. It doesn't matter if the wire is straight or if the wire is a loop or what's happening. You have a wire with a current flowing in it. I'm going to have mine going up. I put my thumb in the direction of the current and my right thumb in the direction of the current, and my fingers roll around in the direction of the magnetic field, forms a circle. So if I'm standing at the tip of my finger with a magnetic field probe, the magnetic field is pointing toward the camera. If I'm on this side, it points away from the camera. We good with that? Now, if I have a loop of wire and I have a current flowing in this direction, what is that, clockwise? I just pick any little segment. I'm going to take this little segment right here, stick my thumb in the direction of the current. I know the magnetic field forms a circle around it. So if I'm on the interior of that loop, it points away from the camera. If I'm on the exterior, it points toward the camera if the current is going in that direction. Then I can do it anywhere. I can do it at the top of the loop. I'm going to get the same result. If the current is going that way, to the right, put my thumb in that direction. Anywhere outside the loop above my thumb, the magnetic field points toward the camera. Anywhere below it, it's going into the loop, away from the camera. We are going to do some calculus today, yes. All right. Let's fill this in then. So our loop carrying a current I has a magnetic field that is out of the page, anywhere within the loop, and into the page on the exterior. Let's rotate the loop 90 degrees. Maybe this will help. Here's our loop of wire. We're going to rotate it 90 degrees, okay? And we're going to draw it like this. All right, so this was our loop up here. You see it up here? That's the loop. We're going to rotate it 90 degrees and look at it on end. So what do we see when we look at it like this? We see current coming towards us on one side and away from us on the other side. So I'm going to put a dot here. Let's see, how do we want to do this? I want to do it, I'm going to have it I'm going to have it coming toward me on one side, this side. It doesn't matter. I'll rotate the bottom of the loop toward the camera, and now this should be the right orientation here. You see that? So let's just pick a side. On the left, the current is coming toward us. Current is coming toward the camera on the left. So I put my thumb in the direction of the current, and if I know I'm going to get small circles forming around it that make the magnetic field, something like this. And I need to know which direction they go. So I've got my thumb in the direction of the current, and it tells me that everywhere on the interior of the loop, the magnetic field is pointing up, and everywhere on the exterior of the loop, it's pointing down. I can do the same on the other side. I know I'm going to get circles forming around this. Those are kind of circles. I put my thumb in the direction of the current. Now I'm on this side of the loop, right? The current is coming toward me, away from the camera. I put my thumb there. It's a little hard. My fingers wrap around outside. It's going into the page. And in the middle of the loop here, it's coming up out of the page. You better get the same result on both sides or you're doing something wrong. All right, now let's redraw this. Let's redraw those magnetic fields a little bit. Fill it in. It basically looks like this. Down the center, oops. Yeah, that's good enough. Down the center, we've got a field line that's doing that. And over here, we've got one that's doing kind of that. And then we've got one maybe that's doing something like that. And one that's doing, anyway, something like that, right? Now that should look a little familiar. What happened? The solenoid, well, this is a solenoid basically, right? This is a one-turn solenoid. Yeah, it looks like a solenoid. This is a one-turn solenoid. But what happened when we did a permanent magnet, remember? We had a north, let me stick with blue for my magnetic field lines. Okay, they originate on north poles, terminate on south poles. Magnetic field lines want to form loops. They want to close on themselves. So these look very similar. If I made my magnet really small, then it would look identical to this. Or if I added a few extra loops to my wire here to make it more like a solenoid, it would look more like this a permanent magnet. But it's basically acts like a permanent magnet with a north and south pole. Okay, did that help a little bit? Let's see how current carrying wires interact with each other. We've got wire 1 over here carrying current. And we've got wire 2 over here, which we have it in the same direction. Now, what's going to happen? Are they going to interact with each other? Two long parallel current carrying wires. All right, let's think about it. Why would they interact with each other? One of those wires carries a current. What's it doing? It's filling the space around it with a magnetic field, right? Now the other wire is carrying a current in the presence of a magnetic field. It may feel a force because of that. So let's think it through. Let's say wire 1 is filling the space around it with a magnetic field. Of course, they both are, but we can do it one at a time. So wire 1 fills the space around it with a magnetic field. That means, excuse me, that means that we've got a magnetic field that looks like this. B, I'm going to say B from 1. And as we move farther away, that magnetic field gets a little weaker. These lines become farther apart. And if we're all the way over here, that magnetic field looks like this. Okay, so standing on wire 2, what does the magnetic field look like? Straight up. Right, we draw it as a circle, But really, if you're standing on that circle, it points tangent to the circle, right? The circle just gives us a direction. But at any one of those locations on the circular path, it points tangent to the circle. So our current is out of the page. I2 is out of the page. The magnetic field that I2 is sitting in, right, the magnetic field due to wire 1, points toward the top of the page. I cross B is in what direction? This direction. This is force from 1 on 2. And we could do the same reasoning in the other direction. We've got, let's see, I'll use green. We've got a magnetic field over here from 2, and that means we're going to get a force from 2 acting on 1 that points in the other direction. Okay, so these two wires attract. Okay. We got two long current carrying wires parallel. If the current is in the same direction, they attract each other. If the current is in opposite directions, then they would repel. You can work through the same reasoning. Draw out the the magnetic field from one wire at the location of the other wire, right? You just say to yourself, wire 1, all wire 1 is doing is filling the space around it with a magnetic field. Wire 2 is carrying a current in a magnetic field, and it feels a force because of that. And then you reverse it, and you say wire 2 actually is also filling the space around it with a magnetic field, and wire 1 is carrying a current in that magnetic field, and figure out the forces. It turns out that if the currents are in the same direction, you get attraction. The wires attract. If they're in opposite directions, then the wires repel each other. I can never remember that. I have to work it out every time like this. Okay, we ready for some calculus? That's not the right answer, Brent. Answer is yes. Okay, well, ready or not, ready or not, here it comes. Okay, let's take a quick look at this in a little more detail, because I've just been drawing the magnetic field lines, but as sort of constant or just one magnetic field line. But we know that it's going to drop off, right? As you go away from that current carrying wire, the magnetic field is going to get weaker and weaker. So let's try to get a visual on that. Let's see. Let's put it right here. Here's our current. So we're going to get a magnetic field that forms around. There's going to be a line right there. And then let's make the next one. How about here? Oops. And the next one might be out here. And the next one's going to be over here somewhere. You get the idea? The lines are getting farther apart as our radius gets bigger and bigger. Okay. So our law here, our rule, or our equation is the Biot-Savart law. All right. And you can start with moving charges and work your way up to currents, but we always deal with currents. So let's just start with this equation. Some books write it this way. Some books write it as ds cross r vector over r cubed. But that's exactly the same as writing it as ds cross r hat over r squared, right? Because r hat is a unit vector that points in the r direction. R vector has magnitude. So if you divide it by the magnitude of r, then you get r hat. You okay with that? Mu naught is a constant that we get in all of our magnetic equations, just like we had epsilon naught in most of our electrostatics equations. Mu naught is in most of our magnetic equations. Mu naught is equal to 4 pi times 10 to the minus 7. Tesla meters over amps. And I think you found mu naught, if I'm not mistaken, when you did the magnetic field of a solenoid. Magnetic field of a solenoid, you said the magnetic field is proportional to, what was it proportional to? The number of turns, and it was proportional to the current, and it was inversely proportional, right? So it was proportional to 1 over the length, and there was some constant out in front. And that constant was mu naught, 4 pi times 10 to the minus 7. Okay, let's move on. So this equation looks a little scary at first, but its bark is worse than its bite. It's not too bad. Let's just walk through it and see how we use it. Okay. We'll start out with a straight line. Let's make it an infinite find the magnetic field near an infinite straight current carrying wire. All right, so here's our wire. Our wire is going to be along the x-axis here. I need a... how's that? And we want to find the magnetic field up here. We'll just pick a point on the y-axis. And let's call that capital R. Normally, I leave it as a lowercase r as a variable. And then in the end, I say, well, r could be anything, right? This gives me b as a function of r, the distance away from the wire. But I can't do that because I have a little r in my equation here, right? I've got this little r here, so I can't have two at the same. I'm going to stick with the equation. The equation has this little r here. Let's stick with that, and we'll call our variable capital R. At the end, we'll say capital R is a variable. We could be far away from the wire or close to the wire. It'll be a function of capital R. So this is telling us, as always, what do we do when we're finding the contribution from a whole bunch of stuff, right? Like from a charge distribution, a whole charge distribution. We break it up into some little infinitesimal chunk of charge, right? dq, and then we add up, treat that like a point charge, right? And we add up all the effects, and that's how we get our total field. We're doing the same thing. Biot-Savart Law is the same thing. It starts out, if you look at the derivation of the Biot-Savart Law, it starts out with one charge moving. How does that one charge create a magnetic field around it? And then it turns that into a current. And what we're doing is we're taking ds is a length element. ds is some little tiny length of the total current path. And then what are we doing? We're adding up all the little length segments of the current path to get the total contribution to the magnetic field. So just like finding that dq, remember one of the first things you did when you had a charge distribution, you just picked some arbitrary little chunk of charge, called it dq, and helped set up a drawing. What's r, what's theta, you set up your drawing that way. We're going to do the same thing here. Let's pick some arbitrary little chunk right here. I'll pick this little chunk right here. This is going to be ds, and its points, ds points in the direction of the current. Right? It's a vector. It has direction associated with it. Okay, so let's walk through these. So here, let me write out the equation one more time. The equation B is equal to mu naught I over 4 pi integral ds cross r hat over r squared. And let's just walk through each one of these things. Mu naught, we know what mu naught is, right? It's a constant, 4 pi times 10 to the minus 7. I is our current. It would be given, I guess. Four and pi, we know what those are. Those are constants. ds, what would ds be in this case? It's a length element. And since our wire is straight and it's in the x direction, let's call it dx. And let's look at ds cross r hat. Let's draw in where r and r hat are. R is the distance from ds to our point of interest. And it's also a vector. It points from ds to our point of interest. So r would be this one. Let's see. I'll use green. R would be this vector right here. And that means that r hat is this little unit vector that points in that direction. So far, so good. So we know mu naught I, we know ds. In our drawing here, we know what r and r hat are. R is going to be, let's look at our drawing one more time. Where is ds located? It's located at x, right? And this would be dx here, right? So r is x squared plus capital R squared square root, right? We've got a right triangle there. Again, these are a lot of the same techniques that we used when we had the electric fields, right? We got our dq, made our triangle dx, turned the dq into lambda dx, remember? So it's the same, a lot of the same techniques we use there, we're using here. Okay, where are we? R. So we don't have just an R, we have a ds cross r hat. ds cross r hat, what is that? Well, that's a cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle you get when you put their tails together. When you put those two vectors, when you put their tails together. What's the magnitude of ds? dx. We're just calling that dx, right? What's the magnitude of r hat? 1. It's a unit vector. That's the definition, right? Magnitude 1. It only has direction associated with it. And then we've got this sine theta. But we can get sine theta from our drawing. What is theta? Let's figure out first which angle here is theta. Theta comes from the cross product of ds and r hat. So it's the angle we get when we put their tails together, ds and r hat. When we put their tails together, that is theta. So it's that angle right there. And the sine of that angle is capital R over little r. Now I'm forgetting one thing. The cross product returns a direction, right? It's a vector. The answer is a vector, not a scalar. What direction do I get when I do ds cross r hat here? if this is my x, this is my x, and this is my y, I put my fingers in the direction of dx, roll them toward r hat, I get out of the page, or the z direction, right? So over here, I should really write I should really have a direction associated with it. Remember, the x, y, z coordinate system is a right-handed coordinate system. So if you never can remember what direction, given x and y, what direction z points, is it out of the page or into the page? It's a right-handed coordinate system. It's a cross product between x and y, basically, to get z. So you put your fingers in the direction of x, you roll them toward y like you're doing a cross product, and your thumb points in the direction of z. All right, we have everything. We ready to integrate? Let's start plugging them in. B is u naught I over 4 pi integral. This is going to be dx dx r over r over r, right? And that's going to give me integral of r dx over little r cubed, and little r is x squared plus capital R squared square root, so I get the 3/2 power. R squared, thank you. R squared, not r. And then I end up with an r cubed, and r is to the 1/2, so I get the 3/2 power. Now, what are my limits? What are we integrating over? The current path. So negative infinity to positive infinity. All right. Let's just finish this off, and then we'll take a little break. Because this is symmetric, we can just go, sometimes it's easier, sometimes it's not. 2 times the integral from 0 to infinity. This is symmetric, we can do that. You can't always do that. And I looked this up on my table of integrals on my formula sheet. Let me get all the constants out in front first. Then I look that up, and I get, what do I get? X over r squared, x squared plus r squared to the 1/2 power evaluated from 0 to infinity. And that gives me, what does that give me? Mu naught I over 2 pi r x over x squared plus r squared to the 1/2. And this is 1. I get mu naught I over 2 pi r. So in general here, I can just okay, we can get that from Biot-Savart Law. It's not too bad. But it doesn't have to be an infinite. The nice thing about this formula, it can be any segment of wire. It just, the limits change, right? The limits change. Yeah, I changed my limits. I multiplied by 2 and changed it to 0. It's the same thing. You can do it either way. Direction. So the direction comes from, you can do it 2 ways. The direction comes from the cross product. ds cross r hat gives you the direction, or you can use your right hand rule where you stick your thumb in the direction of the current and you say that anywhere above this wire, it's going to be coming out of the page. Everywhere below the wire in the plane of the page, it's going to be going into the page. Yeah, for this, for the actual calculation here, I left capital R as my variable, how far away from the wire I'm going to be, because I have a little r that is in my equation as a variable. We always use that little r in our equation as a variable. So I used a different thing. But usually when we see this formula, we're thinking a variable. We're thinking, you know, because capital letters typically aren't variables. Lowercase letters typically are variables. So this is our variable, our distance away from the wire. Okay, let's take a 10-minute break. I'll pause the recording. Are we ready for another example? Let's do a one where we don't have an infinite line. Oops. And our current, we can go, how about clockwise, square current loop. And we'll let this be A, minus A. So we'll find the magnetic field at the origin due to one side, and then we'll multiply it by 4 at the end. Because it's symmetric, they're all going to contribute the same amount to the magnetic field at the origin. If I can, I always try to choose a ds that gives me an r that forms an angle theta that's less than 90 degrees, because it's easy for me to see what the sine and cosine of an angle less than 90 degrees are. So I would pick my ds to be this little chunk. Let's just do the bottom. We'll do the bottom chunk. If you pick a ds on this side, your r hat is going to point back there, and you're going to get an angle greater than 90 degrees. It's a little hard to spot what the sine of that angle is. So I like to pick my ds over here, and it doesn't matter where, just any arbitrary little chunk. And that means my r hat, my r vector, will point from ds to my point of interest, the origin. And my r hat will be this little vector right here, the unit vector that points in that direction. And theta will be the angle when you put their tails together, r hat and ds. So let's write all that out. Let's see, what do we know here? Of course, we know mu naught and I. Let's just look at our what's in the integral here. ds, in this case, what's ds going to be? We'll use dx because it's along the, it's aligned with the x-axis, right? ds cross r hat is going to be the magnitude of ds, the magnitude of r hat, and the sine of the angle when we put their tails together. So that's dx and 1. And that's going to be dx times a over r, because the sine of theta, if we go back up here, the sine of theta is A over R. And what am I missing? R. What's R? R is A squared plus X squared. R is X squared plus A squared square root. Now I've got everything. I can plug them into my equation in the integral there, plug it in. Let's just go back. What direction is this magnetic field going to be at the center of that square current carrying loop? First, do the ds cross r hat. What direction does ds cross r hat give you? From ds cross r hat, you put your fingers in the direction of ds, roll them toward r hat, you get into the page, into the page. Now from our other right-hand rule, where we put our thumb in the direction of the current, and we look to see what direction the magnetic field curls around the wire, we see that everywhere above this segment of the wire, the magnetic field will be going into the page. Everywhere below it, it'll be going out of the page. And if we work our thumb all the way around the loop, we always get into the page as the direction of the magnetic field within the loop. So think about both of those. Think about the ds cross r hat, give you the right direction. Think about the other right-hand rule where your thumb goes in the direction of the current and your fingers wrap around the wire in the direction of the magnetic field. And they both should give you the same answer. So we're ready to integrate. We've got all of our, there's our formula, the Biot-Savart Law. We know what ds is, what ds cross r hat is, all this stuff, r, sine theta. So we can plug some things in here. We get b for one side is mu naught I over 4 pi integral of a over r dx over r squared. We know what r is, so we can plug that in. A is a constant, we can bring that out. And we're integrating along the entire segment from minus A to plus A. We're integrating that entire segment, every little segment of that current carrying wire path. We add them all up from minus A to plus A. And we look that up, get the answer. I don't have it here in front of me. And then we say the total magnetic field is 4 times the magnetic field due to one side. we did two different examples. We did an example with a straight wire that went from minus infinity to plus infinity. We did another straight wire that went from minus a to plus a, so just a segment, a finite segment. And we can do anything in between. Now we want to look at a curved segment. What happens when we have a curved line segment? There's our picture. Current comes in along the x-axis from infinity, and we'll call this, what are we going to call this? A and B. This will be B, and this will be A. So comes in, follows a curved path, then comes in towards the origin, follows another curved path, and out to infinity again. What are we going to do to solve this problem? Break up the segments. Think about one segment at a time. I'm going to number them. I've got 1 coming in from infinity, 2 coming the larger arc section, 3, 4, and 5 going out to infinity again. So let's look at them one at a time. Segment 1, we've got our current in this direction. So we can pick a ds. And where's our point of interest? Our point of interest is in line with the current. R hat and ds point in the same direction. There's no perpendicular distance away from the line of current, so the magnetic field at the origin due to this current is 0. ds cross r hat is 0. Let's take a look at segment 3. what's happening on segment 3? ds and r hat point in the same direction again, right? Their current path points right at our point of interest. There's no perpendicular distance away from the line of the current to our point of interest. We get 0 again. And let's do one more. Segment 5. Segment 5, ds is pointing out towards negative infinity. R hat is pointing toward the origin. We get a sine of 180 degrees. We get ds cross r hat is 0. So I did the 3 easy ones first, right? We've got 0 for segment 1, segment 3, and segment 5. Now let's do the curved segments. It turns out that this is really simple. The calculus simplifies very quickly when we have a curved segment like this. So let's take a look at what happens along segment 2. Segment 2 looks something like this. Current is in this direction. My ds looks like that. My point of interest is over here somewhere. So r hat points this way. And these are 90 degrees apart. ds cross r hat, anywhere on that line, ds is tangent to the path, and r hat points towards the origin, which happens to be the center of that circular arc, always 90 degrees apart. ds perpendicular to r hat. So, what's ds cross r hat? Just ds, right? It's ds times the magnitude of r hat, which is 1, times the sine of 90 degrees, which is 1. It's just ds. Now what do I have? I've got my magnetic field is mu naught I over 4 pi integral of ds cross r hat. I'm just going to write it out. Over r squared. I know, well, we'll do it on my next step here. ds cross r hat is just ds, and it is into the page, right? And what is r? R is constant. We're moving on a circular path, a circular arc length. R is constant, and in this case I said it was b. So it's constant, and we're just going to call it lowercase b. That means it comes out of the integral. Mu naught I over 4 pi. The b squared comes out. And we just have the integral of ds. What is the integral of ds? S, the arc length. S is 1/3 of pi r, right? And r is b. So I plug that in. I got mu naught I over 12b into the page. If you prefer, let's go back up here for a second. If you prefer the integral of ds, you can substitute in r d theta, and we were going from 0 to pi over 3 here, I think. 60-degree angle, right? 0 to pi over 3. And so you get r is a constant. Integral of d theta is just theta. And we're going from 0 to pi over 3. We get the same thing. Okay, however you like to think about it. If you want to plug in the r d theta for ds, go ahead and do that. If you see ds and you go, oh, the integral of ds is just s is the arc length, and put it in that way, that's fine too. All right, so there's segment 2. I'll call it B2, B sub 2, segment 2. We have one more we have to do. And segment 4, we're going to get the exact same thing. Mu naught I over 12, except now the radius is A, and the direction will be the other way. You can go through, practice going through it, following the steps I did in the previous segment, and see if you get this same answer. So B total it's vector addition. We add them all up. How many segments? 5 segments. We got 0. We got positive, if positive is into the page. Zero for 3. We got out of the page, negative mu naught I over 12a, and 0. We added them all up, and there's our answer. Okay. When you first saw Biot-Savart Law, where is it? Here. When you first saw this, looks a little scary, right? Looks a little intimidating. But we break it down, we look at one thing at a time, and it's not so bad. We can do this for straight line segments, right? And it's very similar. The formulas that we get, the substitutions we do, very similar to the techniques we used when we found the electric field due to charge distributions. Now, when we got to a curved path, it turned out to be really simple because ds cross r hat is always 90 degrees perpendicular. ds and r hat are always perpendicular to each other. So ds cross r hat was just ds. R was a constant because it's a circular arc length. R is a constant. It comes out of the integral. And all that stuff ends up just being the integral of ds, which is the arc length s. So it really simplifies nicely. Go through it a few times and make sure you understand how that all works. Let's practice the right-hand rule one more time. And I want you to think about both using ds cross r hat to find the direction of the magnetic field at our point of interest, and using our old standby where we put our thumb in the direction of the current and we let our fingers wrap around in the direction of the magnetic field, and see if you can get the same direction both ways. So we want to know the magnetic field at that location. We've got a current carrying wire, and we're going to pick some little element ds. So when you use ds cross r hat, what direction do you get for your magnetic field? Out of the page. ds cross r hat out of the page. Now, if you just run your thumb along the wire in the direction of the current, everywhere above the wire, you get that it has to be coming out of the page. And everywhere below the wire, you get that it has to be going into the page. So either way, we get the same answer. Think about it, practice using both, see what you like better. Okay, let's do another one. Pick some element here. ds cross r hat is what direction? Out of the page. Put your fingers in the direction of ds, roll them toward r hat, your thumb points out of the page. Now, using our other technique, we put our thumb in the direction of the current, your right thumb, in the direction of the current. Everywhere to the right of this wire, the magnetic field is coming up out of the page. Everywhere to the left of it, it's going down into the page. Let's do a couple of more. There, I is a long wire perpendicular to the page. The current's coming out of the page. What direction is ds cross r hat? ds would be pointing out of the page, same direction as the current. R hat would be pointing to the place of interest. So ds cross r hat would be towards the top of the page. In this case, it's probably better to use the other right-hand rule. Put your thumb in the direction of the current. Your fingers roll around in the direction of the magnetic field. So at this point, what direction is the magnetic field? Toward the top of the page. Good. Let's do another one. Let's do a loop. And we are interested in the magnetic field at the center of the loop. Pick a place. Where should we pick? How about picking this spot over here? DS is over here. What direction is r hat? R hat points from DS to our point of interest, where we want to know what the magnetic field is. So DS cross r hat is out of the page. Now, it better be the same no matter where we pick a DS, right? Let's pick this DS over here. I'll make it gray. Using this one, where's my r hat? Points from DS to my point of interest. DS cross r hat is out of the page. It doesn't matter where you pick it on here, right? Because in the circular loop like this, all of them create the magnetic field in the same direction. Sometimes it does change direction, like we saw earlier with this situation. Where was it? Right here. Segment 2 created a magnetic field that was into the page, but segment 4 created a magnetic field that was out of the page, right? It flipped because the current kind of changed direction and it was on the same side of our point of interest. But when we have a closed loop like this and we're looking for the magnetic field inside the loop, they all end up giving you the same direction. And our other right-hand rule, put your thumb in the direction of the current, wrap it around that wire loop, and everywhere on the interior of the loop, your fingers point up out of the page, and everywhere on the exterior of that, they point into the page. Okay, good. Let's move on. I told you we were following very close the methodology we used in finding electric fields from charge distributions. You can sort of treat it like the electric field is from a point charge, and then you integrate all the little DQs, right? Here, I know we didn't really start with that, but if you look up the derivation for the Biot-Savart law, it starts with the magnetic field from a single charge that's moving, and then they turn that into a current carrying wire. We never really do it for a single charge, so I just jumped right to the current carrying wire. But what was the next thing we did? We said we had this special relationship, Gauss's law, that only really helped us in a few cases, but in those few cases it was really helpful, right? Well, it turns out we have an analogy with magnetic fields. We have Amperes' law. And again, it only helps us in a few cases, but in those few cases, it's really helpful. So let's take a look. We know that a current carrying wire fills the space around it with a magnetic field, and we know it's the direction, right? We even know the answer. We know that B is mu naught I over 2 pi r for an infinitely long, straight, current carrying wire. Now let's integrate B around this path. So around the closed path, B dot ds, B is in the same direction that we're going around the path, so the cosine of 0 degrees is just 1. We can get rid of our dot product. B is constant on that special circular path that we chose, so it can come out of the integral. This is for a circular path around a single wire. We're choosing a very special path because we know it's easy, right? We know the answer already. Now, the integral of ds is just the arc length. We're going all the way around the circle, so it's the circumference of the circle, 2 pi r. And if we cheat a little bit, we know what B is, right? B is mu naught I over 2 pi r. So we get mu naught I. It turns out that this works for any path. We picked a very special one, I know, around a circular path, around an infinite wire. Amperes' law is the integral around a closed path of B dot ds is mu naught times the I enclosed by that path. The total current enclosed by the path integral. Where is this helpful? Let me tell you. Infinite straight wires. And solenoids. And that's it. So our Gauss's law was good for only a few cases also, right? Spherical symmetry, cylindrical symmetry, and infinite sheets. 3 cases where we could use it. Here, we really only have 2 cases where we use it. It's very specialized, but in those 2 cases, it makes it very easy to find the magnetic field. Now, for the first case, we could have just integrated over that field anyway from minus infinity to positive infinity, right? Integrated over the current path, I should have said, from minus infinity to plus infinity. And we can get the answer. We did it earlier today. But this is a little quicker and easier. The solenoids, I'll show you an example of that. Very nice way to get the magnetic field inside of a solenoid. But let's do another example where we could use this. As long as it's an infinite straight wire, we can find the magnetic field inside of the wire now. So let's take a look at that. A long straight wire with current I uniformly distributed over the cross section of the wire. So let me draw it for you. The wire has some dimension now, right? Some thickness to it, a diameter. It's carrying a current I. And if we look at the cross section, the current is coming toward us. We want to find B everywhere. Find the magnetic field everywhere. Should we do the easy one first? Yes, always start with the easy one. R greater than the radius of this thing. This is radius R. We could use Biot-Savart Law, integrate from minus infinity to plus infinity, but let's just do it with Amperes Law. I'll show you it's 2 lines, 3 lines, we're done, no integrals to look up. Integral around a closed path of B dot ds is mu naught I enclosed by that path. We are going around, I'm just going to draw it as a small dot there. We're going around a path here. B is going to be constant. The entire current inside the wire is enclosed by our path, right? The entire current. So I'm just going to call it I. This is B times 2 pi R. And what do we get? We get B is mu naught I over 2 pi R. We're starting to get familiar with this equation now. We're seeing it a lot, right? B is mu naught I over 2 pi R when you're near a straight infinite wire. Now we want to know the magnetic field inside of that wire. R less than the radius of the wire. So I'm going to draw my wire with some thickness to it. And our path, we're going to take this path around now, not the big one. We're inside. This is our path for integral B dot ds. The integral around that path, B dot ds, is mu naught I enclosed. The left side is just going to be B times the integral of ds, which is just going to be b times 2 pi r. Now the question is, what is I enclosed? Because the current is uniformly distributed over the surface area, we can just take a ratio of the areas. The area enclosed over the total area times the current. Okay, think about anything. Water flow. If there was water flowing uniformly across the diameter of a pipe, you could do the same thing to figure out how much water was coming out of a certain cross-sectional area of the pipe. But this is current flow, and we can do the same thing. Ratio of the areas, because it's uniformly distributed over the area. And so our magnetic field is going to be mu naught I over 2 pi capital R squared times little r. We could even plot this if we wanted to. Here's the diameter, here's the radius of our wire. And we could look at our magnetic field as a function of r. It starts at 0. It increases linearly, b proportional to r in this region. And then it drops off, b proportional 1 over r in this region. Once you go outside of the wire, it drops off as 1 over r. All right, that's a good ending point for today. Practice with Biot-Savart Law and Amperes law, and we will continue with magnetic fields next time.